Today we're going to start on chapter 5, and chapter 5, things get a little bit more complicated. We're going to talk about electricity, magnetism, electromagnetism. So what we're going to do is we're going to break that up into 3 different lectures, or at least 2. We'll talk about electricity, and we'll talk about magnetism, and then we'll talk about electromagnetism and how it is that we take relatively low voltage and manipulate it to create high voltage in order to make X-rays. So a lot of what we're going to talk about from now to the end of the semester we've already touched on at least once. So we're going to get more technical with it and further explain what's going on in the imaging system in order to create X-rays. So I just want to read the first part of chapter 5 on page 70. And we're working out of Bushong's Radiologic Science for Technologists. It's 13th edition. It's their 50th anniversary. It's a gold book. So the first line there says the primary function of an X-ray imaging system is to convert electric energy into electromagnetic energy. Now I want to stop right there and I want you to flip over to page 130 because on 130 it's going to say something that sounds like it might be a little bit of a contradiction, but it's not. So on page 30 the chapter starts off under electron target interactions within chapter 6, or chapter 6 emphasizes the primary function is to accelerate electrons from the cathode to the anode in the X-ray tube, which are both true. So the entire imaging system, what we're doing is manipulating the energy levels, the voltage and the amperage, to give us precisely how many electrons that we need in what energy level we need them to travel across the X-ray tube to slam into the anode and to create the X-rays in the energy level that we need the X-ray photons. So both of them are true. But it goes on to say electric energy is supplied to the X-ray imaging system in the form of well-controlled electric current. Current is amperage. Amperage just means the number of electrons we send. A conversion takes place in the X-ray tube where most of the electric energy is transferred into heat, which is true. Upwards of 99% of what we create in the X-ray tube is heat. We do create just a little bit of light, but that light comes from that heat, those hot electrons, and then the remainder of it is X-rays. So that's the start of chapter 5. So what we're going to talk about in chapter 5 is we're going to define electrification. We're going to look at what electrostatics is, identify the units of electric current, that's amperage, electric potential, that's voltage, and electric power, which is wattage. So current times potential equals watts in electric power. We're going to identify the interactions between matter and the magnetic field. So how it is that we use electrons to create a magnetic field. And in that we can manipulate the power level, the current, and the voltage. We'll talk about the 4 laws of magnetism. We'll talk about the experiments of Oersted, Lenz, and Faraday, and how their contributions, or what their contributions were to the understanding of electricity. And then we'll identify the laws of electromagnetic induction. So electrostatics, before we really get into this, we need to make a clarification about what electric charges are. So just look at the word itself: electrostatics, electrification, electricity. All of those start with electra, which you carry it out just a little bit further, and it's electron. So everything that we're going to talk about is going to involve the movement of electrons. And it's an important distinction to make because you have positive charges, you have negative charges. And the positive charges in every atom is those positive charges are contained within the nucleus of the atom. So the nucleus is what determines what the atom is. So how many positive charges you have determines the element that you're working with. So you can't really move the protons. The protons are fixed in place. So most of the time what we're going to be using for electricity is going to be copper wiring, or some other kind of metal wiring. Most of the time it's going to be copper because it's efficient and it withstands a lot of heat. So most of the time it's going to be copper. So we can't really move the protons. Protons are fixed into place when we supply more, charged particles to the wire. We're not pushing protons, because if we would push protons, we would either change the wire or we would be moving the wire, one of the two. So when we're talking about electricity, we're always going to be talking about charged particles, certainly, but it's specifically going to be the electron. So electrostatics is study of stationary electric charges, and those charges, they don't stay static for long in a lot of cases. So where we're most familiar with static electricity is in the wintertime. In the wintertime, the humidity drops. It gets colder, the humidity drops, and if you move across your carpet or you move across the upholstery in your car, then what you'll do is you'll scoop up electrons. That's one of the ways that we get electrified. And it's not the same as electrocuted, but that's a way that we get electrified. We store electrons because we've scooted across the upholstery in the car. So we store those electrons, but whenever you touch something, what you'll get is a static discharge, and that's a little sting you get, the static pop. That if it's strong enough, you can actually hear it. And that's equalization of that electric charge that you stored up. You don't see it in the summertime, because in the summer what we've got is a lot of humidity that absorb those static charges. So you're still sliding across your upholstery, you're still trying to pick up electrons, but you just discharge those all the time into the air, into the humidity in the summertime. In the wintertime, it's not that way. Also in the wintertime, you notice that the air is so dry that your skin gets kind of dry and scaly, and sometimes it cracks. So you apply a little bit more lotion or moisturizer to your skin. That's going to be a whole lot worse for you starting in healthcare, because you're going to be washing your hands a lot. So make sure that you carry around some sort of moisturizer. The only thing that works for me, I have dry skin, and in the wintertime my skin can actually crack and bleed, especially right on the edges of my fingernails. O'Keeffe's Working Hands. It comes in a little green tub, or there are some tubes as well. It's just about the only thing that works for me that's practical. The other thing that works for me, and it may work for you as well, is if you find this on the laxative aisle, but it's mineral oil. So mineral oil is basically oil. Mineral oil is basically baby oil without the fragrance added to it. So before O'Keeffe's came out, what I would do is I'd wash my hands, and I'd leave my hands wet, and then I'd put mineral oil on my hands, and I'd rub that in and dry my hands. And it worked pretty well. It's just not practical for the workplace. You can't really carry around a jar of mineral oil in your pocket. If it comes open, you're going to have a mess. So O'Keeffe's Working Hands. This is not a plug. I'm not sponsored by anybody, but O'Keeffe's, if you're listening, I'm open to suggestions here. But keep some on you, something that works for you. So electrification can be created by three different ways, really. And we talked about one, that was friction. You slide across the carpet, or you slide across the upholstery, and you pick up electrons. And that is electrification by friction. And then you've got contact and induction. So contact would be where two things come together, and you've got a surplus of electrons, and you've got maybe not a lack of electrons, but you've got more electrons here than what you have on the other side. Imagine you've got, 10 balls in one hand and 2 balls in the other. You can carry the 12 balls easier if you put 12 or 6 and 6 in each hand, right? Well, that's kind of how contact would work. So two things come into contact, and it equalizes so that you don't have as strong electrostatic charge on one side. And then the other is induction. and induction is kind of what you get in a lightning strike, and really it's what you get in a static electricity charge once you scoop up those electrons. In most cases, before you make the contact with whatever you're reaching for, you'll get a spark that jumps from you to that thing, and you're letting go of those electrons. So in a lot of cases, we don't have to have the contact. We get induction. If you get close enough, those electric charges will jump. So there's 4 laws of electrostatics, and that is unlike charges attract and like charges repel. So we've seen this already earlier in the semester. So what we're dealing with then in this case is all static charges, static electricity charges, and all electrons. So they're all the same charge. They're having a tendency to push each other apart. So hang on to that for a second. So electric charge of a conductor is concentrated along the sharpest curvature. So let's say we've got this thing, right? This is actually my charging cable, and let's say we've got electrons all the way across the top of this and all the way across the bottom of it. So if I curve it up, what's going to happen is, this is just a visual thing. Imagine that each one of the electrons are maybe the size of a penny. And if I were to bend it down like this, what's going to happen with the pennies on the bottom side, they were spaced out, and now they're going to be scrunched together. And the ones on the top were a little bit spread out, and now they're even more so. So what's going to happen is that some of the charges will come up from the bottom side to the top side, because we're pushing them together. They're all negative charges. They don't want to touch each other, so they're going to kind of push each other apart. You make room on the top, and the ones on the bottom will actually go to the top. So hang on to that for a minute. So electric charge distribution is uniform throughout or on the surface. So that seems to contradict the one directly preceding it. So electric charge of a conductor is concentrated along the sharpest curvature, but electric charge distribution is uniform throughout or on the surface. So now we straighten our conductor back out, and what we've got is a flat line. And electricity is kind of like water, or in ways we can use water as an analogy for electricity. So you pour water on the floor and it finds its own level, or you pour it in a pot or in a pan or something, and it finds its own level. It doesn't just stack up. And the same thing applies to electric charges. They distribute as smoothly and evenly as possible. So they're not really a contradiction. It's not until you get that curvature that you get the concentration. So unlike charges and like charges, law number 1. The second one is concentration. The third one is distribution. And then the fourth one kind of has a couple of parts to it. So electrostatic force is directly proportional to the product of the electrostatic charges. And stop there. So what does that mean? Electrostatic force, the force of the electrons, the force of the power of the electrons, the concentrated electrons. So what that means is the electrostatic force is directly proportional to the product, and product being mathematical addition of the electrostatic charges. So what is an electrostatic charge? It's just electrons. So you have one electron, you have one electrostatic charge. You have 2 electrons, then your electrostatic charge is 2. So you have 4, then you got 4. So what that means is the electrostatic force is directly proportional to the product of the electrostatic charges. What that means is the more you have, the more you have. The more electrostatic charges you have, the more electrostatic force you have. So you stack up a lot of electrons, you push them close together, then you've got a pretty good electrostatic charge. You've scooted across your upholstery in your car once, and you got a pretty good little electrostatic charge. And let's say you scoot across it twice. You get in, you get out, you get in, you get out, then you're going to scoop up more electrons, and that electrostatic charge that you've got in your body now becomes a little bit more significant. So again, going back to the idea of the induction, whenever you get close to something and that electric charge jumps, your electrostatic charge is higher when it jumps, and it hurts more and you can actually hear it. You have more electrons. So you have more electrons in your body, your electrostatic charge is higher, and you can feel that whenever those electrons jump. So that's the first part of the law number 4. Electrostatic force is directly proportional to the product of the electrostatic charges. The more charges you have, the more force you have. And it's inversely proportional to the square of the distance between them. So that's just the inverse square law all over again. So what that means is that if you have 2 electrons and they're pushed as close together as possible, they have more potency than 2 electrons that are far apart. So the electrostatic charge is directly proportional to the product of the electrostatic charges. The more you have, the more you have, and inversely proportional to the square of the distance between them. The more compact they are, the more pressed together they are, the more likely they're going to be able to do some sort of work or give you what you want. So the electrostatic force increases as the distance between those electrons decrease. I'll show you a couple of videos that kind of illustrate the potential dangers of static electricity as it pertains to you, especially in the wintertime. So in the wintertime, remember, you build up static charges because there's not the humidity in the air to absorb those static charges. And what happens is you go to pump your gas, right? So you go to pump your gas and you get out of the car and you select your fuel type, you insert your credit card, you do all the things that you have to do, you're touching things. So you discharge those static charges, even if they're little charges, you get rid of them. And you start your gas, and sometimes you may want to go get back in the car. And the problem is you get back in the car and you scoop up more of those electrons. So you're becoming electrified again because of rubbing, right? So you've got those electrons again, and then you go out and let's say you don't want to fill your car completely up, but rather you just want a certain amount of gas. So this guy, he reaches down and he touches the gas pump and a spark comes out, and he makes the mistake of trying to pull, and it's logical, it seems like it's logical anyway, okay, I got to get the gas pump, the gas nozzle out of my car. Well, a couple of things. One is that he could have avoided that by touching the car before he touched the pump handle. And in doing so, what he would do is discharge those electrons back into the car. So then he could touch the gas pump nozzle and there wouldn't be that spark. The demographic that this happens to is almost always young people your age. So you notice older people getting out of the car, they kind of groan and they touch things and they grab door frame and whatnot. They grab the door itself, sometimes pull themselves up out of the car. So they're discharging those electric charges. You're young enough that you've got the quad strength just to spin around, stand straight up. So you're still holding on to your electric charges. This can happen at any gas pump in the wintertime, and it can get really, really nasty. Let me find another one. I'm skipping over one specifically. Here we go. Static electricity sets car on fire. So again, the person grabs the gas pump, and your reaction, your initial thought is, I got to get the gas pump out of the port in my car, right? And the problem is the gas is still spraying. So as you pull that thing out, you hose your car down, and next thing you know, the entire gas station is on fire. What you want to do is be familiar with the gas station whenever you pull up. There's always a big red button that you can push that shuts down everything. It'll shut down if this ever happens to you. It'll shut down every gas pump. You just go push the big red button, it shuts down all gas pumps, and that does not become a problem. So gas, the way gas burns off primarily is that it burns off off of fumes. So the fire is not going to extend down into your gas tank. This is the next one I want to show you. The fire is not going to extend down into your gas tank. The fire is going to be contained right there at the edge of where the nozzle goes in. So if you hit that big red button, it kills the pumps, and then you can go pull the gas pump, the nozzle out of your gas tank, and you can just put the lid on your gas tank, and the fire will go out. Fire has to have oxygen. So this woman does almost everything right. Without hitting the big red button, she did it. This is the best outcome she could have possibly had without hitting the big red button. So she kept her head about her, and she didn't burn her car up. So she does that. Now she's going back because it's cold outside. What'd she do? She went and got back in her car. So when she gets back in her car, she scoops up electrons. When she gets back out of her car, she scoops up electrons. What she should have done was touch the door facing and some portion of the car to release those electrons. But she didn't. But she still kept her head. So she gets out. She gets the amount of gas she wants. And poof. Now watch what she does. She's calm enough. She reaches over there and she clicks the gas, the handle on the pump to stop the flow of gas from going into her car, and then she could pull the pump out. So it's a better outcome than the first one or the second one, but it's not as good outcome as she could have had. So what I really recommend that you do is just look for that big red button, hit the big red button, and then you can go pull the nozzle out of your gas tank. So that's a cause of a flash fire because of static electricity. So now electrodynamics, where static electricity, electrostatics is stationary electric charges. Now we're going to talk about moving electric charges. So electrodynamics is the study of electric charges in motion. Still talking about electrons. So we have to talk about some specific type of materials that we can use. So we've got a conductor, an insulator, a semiconductor, and a superconductor. So all of those are in table 5.1 on page 76. So it's got superconductor, conductor, semiconductor, and insulator. All right, so a conductor is anything that will allow electrons to flow. So certain conductors are more efficient than others. Conductors that have loosely bound electrons in their valence bands, that's their outermost loosely bound bands, kind of, when we're talking about the solar system, they're kind of the comets, the orbit of comets into and outside of the solar system. So they're loosely bound, very loosely bound. So a conductor is anything that allows the electrons to flow easily. The problem is that sometimes you'll have something that touches a conductor. So if something touches a conductor, if something else that is also a good conductor touches a conductor, then you'll have what we refer to as a short circuit. So what we have to have in a complete circuit is we have to have a place for the electrons to go in and a place for the electrons to go out. So a complete circuit has an entrance and exit, a positive and negative for electron flow. So if we have a conductor touching a conductor and the second conductor, we've got our circuit, and a second conductor is maybe touching that circuit and then going into the ground, then we'll have a short circuit. So what we have to have is we have to have something around the conductor to keep that from happening. And what we use are insulators. So like the wires, again, this is my charging cord for the computer. what is kind of fabric on the outside, but inside of that would probably be rubber or plastic. Two very good conductors. So, or I'm sorry, two very good insulators. So an insulator is something that stops electron flow. It prevents electrons from flowing where you don't want them to go. All right, so a conductor is usually going to be surrounded by an insulator, so the electrons go where you want them to go. And then a semiconductor is a material that will act as a conductor in certain circumstances, and in other circumstances, it'll act as an insulator. So an example of a semiconductor would be silicone. So silicone, under certain circumstances, will allow electrons to flow, and under certain circumstances it won't. And in a lot of cases, what we have to have in those type of materials is some sort of impurity. So we've got probably a pretty good insulator, and we'll put some sort of impurity into it, and it becomes a pretty good conductor. Water is another example. Water we tend to think of as being a very good conductor. And it's not. Pure water is a pretty good insulator. It's not a perfect insulator, but it's a pretty good insulator. But you don't see pure water in nature. So in order to have pure water, what you've got to have is you've got to have a distillery. So it's got to be distilled water. It's got to be water with no impurities in it. And if you have water with no impurities in it, it's a pretty good insulator. But as soon as you get impurities in it, it becomes a pretty good conductor. So even if you had distilled water and you dropped an electrode in it, or two electrodes in it, you could measure the potential between those two electrodes, how much current's going in between them. It's going to be pretty low. But as soon as you dip your hand into it, then you introduce impurities. The oil in your skin, the salt in your skin, all those things will go into the water, and immediately it becomes a good conductor and you get shocked. So that's why it is that you don't stand in a puddle of water and work on electricity, because it's a very good conductor once it has those in it. And the fourth type that you see in that table, again, table 5.1 on 76, is superconductor. And a superconductor is a type of conductor that's extremely efficient, and because whenever electrons travel through a circuit, they create friction. Friction creates heat. With superconductors, to make superconductors most efficient, we have to keep them very, very cold. So an example of a superconducting magnet that you see in the hospital at all times is an MRI magnet. So an MRI magnet, the magnetism is made by electricity, and we'll get into that towards the end of this chapter. So it's made by electricity, but it creates a lot of heat. So what we use to cool the superconductors in that would be liquid helium, which is close to 300 degrees below zero. So it's very, very cold. So it's kept very cold. So in electrodynamics, again, we've got to have all those things in place: a conductor, insulator, semiconductor. If we'll need that type of material, which we'll get into again, probably not in this chapter, but later on, or a superconductor, and we'll get into those as well. But when we manipulate electricity, then something has to change. So I'm going to skip this slide and I'm going to go down to the next one. So Ohm's law states that voltage, which is your potential, is equal to the intensity times the resistance inherent in the wire. So resistance is resistance to electron flow. So I just mentioned that when electrons travel through a wire, there's friction. Well, that friction is your resistance. So there's a lot of different things that can control your resistance. The type of insulator, like if you have aluminum, it's not as the type of conductor, rather, it's not as good as copper is. Gold is better than copper, even. The problem with gold is obviously it's very expensive. So resistance is inherent in the conductor. So the conductor can be a very good conductor, but it's still going to have some resistance to it. So voltage is equal to intensity times resistance. And in that, if we have increased electric resistance, then we're going to have a reduction in electric current. So you can kind of, again, going back to the water, if we have a big water hose, we have very little resistance to the water flow, and we're going to have a lot of current. So if you have a big pipe, you can put a lot of water through that pipe. But if you shrink that down to a 1-inch pipe, you can't get as much water out of it in the same period of time as a big pipe. If you cut that down to a even smaller water hose, then there's only so much water that can go through that. So the voltage across the total circuit or in any portion of the circuit is equal to the current times the resistance, and that is Ohm's law. So voltage is equal to intensity times resistance. Series circuit calculation, series circuit and parallel circuits are not on the registry anymore, so I'm not going to talk about those very much. I'm just going to define what they are since they're up here. A series circuit is a type of circuit where electricity has to come out of one resistor and go into another resistor. And what I'm talking about in a resistor is anything that you put into the system that uses electricity is a resistor. All right, so think Christmas lights. So you got Christmas lights. Each one of those lights is what we refer to as a resistor. So for the electricity to go to the second light, then it's got to go through the first light. To get to the third light, it's got to go through the first and second, and so on and so forth. So series circuits, the flow of electricity through one portion is sequential. So it's one after another. One thing, then another thing, then another thing. The problem with series circuit is that if, again, back to the Christmas lights, if one of those lights burns out, then the whole string does not work. So they don't make Christmas lights like that quite so much as what they used to, but we used to, get the Christmas lights out, and if we plugged them in and the whole string didn't work, then we had to look at each light bulb individually and see which one was burned out and replace that bulb so that the whole string would work. So parallel circuits kind of overcome that by virtue of you've got a complete circuit and then your resistors go parallel to each other. So a series circuit is in series because each resistor, goes towards the completed circuit. In a parallel circuit, what you've got is you've got the complete circuit, and then you bleed off a little bit for each one of the resistors. So your light bulbs in most of your Christmas lights now, if one burns out, it's not all that big of a deal. The rest of them still stay lit. So electrodynamics. We're going to talk about the electric power is just wattage. That's power is equal to intensity times voltage. That's current times voltage. Current times potential, or amperage times potential. Any way you want to say that. So the P is power, and the power is wattage. So that's your electrodynamics. So we'll pick up there with the next lecture. We'll talk about magnetism, and then we'll talk about electromagnetism. We'll talk about all the laws and the experiments and all that sort of stuff.